Assalamu alaikum.
Alaikum assalam.
So we're gonna continue with lesson 5, and we're going to start 6. 5 and 6 are very similar. So if you're able to do 5, then you're gonna be able to do 6. Okay. So Thevenin theorem, which says any two-terminal linear network. So if you have a network that has two terminals, okay, usually those two terminals, we connect a load between them. We can find equivalent circuit. So a circuit will do the same job, okay. Equivalent circuit, this equivalent circuit is only one source and resistance or resistor connected in series with that source, and the source is a voltage source. And last time we did 2 examples, I think, and 1 exercise. Now we're gonna continue. So here's and we said the reasoning behind finding the equivalent circuit. It's easier to analyze the equivalent circuit. Okay. So this question says find Thevenin equivalent circuit. So at the end, your answer has to be Thevenin equivalent circuit. So at the end, you're gonna say the Thevenin equivalent for this circuit. Okay, the Thevenin. So the Thevenin's equivalent circuit. So this has to be your answer at the end. You're gonna give them the equivalent circuit. Okay, remember that you have to give them the equivalent circuit. So the Thevenin equivalent circuit is the circuit. This is a DC, so the equivalent circuit will be DC, a resistor, a source, and your terminals. This is the equivalent circuit. This is our Thevenin, which is the equivalent Thevenin. And this is E Thevenin. I have to find R Thevenin and E Thevenin, and this resistance here, the R, it's our load. So it is, this resistance is added to the equivalent. It's not part of the equivalent circuit. It's not part of the original network. It's the load connected to the network. Okay, guys, close your mic if you're gonna have some chat with someone. Okay, so 2 steps here. We have to find R Thevenin. Then we have to find E Thevenin. Then once we find those ones, we're gonna plug them here and say this is the equivalent circuit. So if you remember from yesterday, to find R Thevenin, we remove the sources. First, the load is not included in this, so this is always removed. So this is what we have. These are the 2 terminals. Resistance, the load is removed. Then here, this is the current source. This is the resistor, the voltage source, and oops. There's another resistor here. So what I'm gonna do, I have to remove the sources, this source, because I want to find R Thevenin only. So this source is gone, and this source is gone. I replace them with, so current source is replaced with open circuit. So current will be 0 here. short circuit for the voltage source. Now this is 2.2 kilo ohm, and this is 5.6 kilo ohm, and I'm gonna find R Thevenin between the terminals here. Is this okay so far? Any questions up to here? Okay, so now finding R Thevenin here is something that's related to fundamental one. You try to make the circuit look easier. So this is how I'm gonna make it look easier. I'll keep this resistor. Now the open circuit branch, this branch is not gonna affect my analysis. So there's nothing here, no current going through. So this branch, remove it completely. It's okay. So 2.2 kilo ohm. This resistance between these 2 points is exactly like these 2 points. There's no difference. So I can connect it here. 5.6 kilo ohm. And then the terminals where I want to find R Thevenin between these 2 points. This circuit and this circuit is basically the same. This point is 1 point, all this point here, here, and here, which is the same as here, here, and here. And the other point in the bottom, the node, is the same thing. Now, clearly, I can see from this connection that these 2 resistors are connected in parallel, so the total resistance here, R Thevenin, is those 2 resistors in parallel. So I can multiply, divide by the sum, or I can do 1 over, 1 over, and 1 over that. So I can multiply 5.6 and 2.2, and here is 5.6 plus 2.2. I think this gives me 1.58 if I'm not wrong. Kilo ohm, because they're all in kilos. So I got the answer here, 1.58 kilo ohm. Any questions so far?
Sir, can you repeat the last step?
Which one? The combination of the 2 resistors?
Yes.
Now, are you able to see that these 2 resistors are connected in parallel here? Now,
Yes.
now resistors are connected in parallel, 2 or 3 or 5 or whatever. If one terminal of those resistors, okay, is connected to one node, and the other terminal of all these resistors are going to another node, like here, this terminal here, and this terminal, you're going to one node. They're meeting. The other side, this terminal and this terminal of the resistors are meeting in one node, so those resistors are connected in parallel. Now, when you have parallel resistors, maybe you guys remember this more, you do 1 over 5.6 plus 1 over 2.2. If you simplify this, you're gonna get this one. So this is just a special case. Product times divided by the sum is just that thing exactly, and this was gonna give you the same answer. This is just a simplified form of that form when you only have two resistors. So this is a special case for two resistors. Now to find E Thevenin, we'll have to find the open circuit voltage. Does that mean I draw the circuit with all the sources and everything? So this is the circuit here. This is the open. This is where the terminals are. So I'm going to find the voltage between these 2 points. E Thevenin. Okay, going to find the voltage between these 2 points. Open circuit voltage. 16 volt here. 2.2K here. The current source is 8 milli, and it is going down, and this resistance is 5.6 kilo ohm. So you're going to use any analysis you want. Okay, any analysis you want. I'm going to use the nodal analysis. Okay, I'm going to use nodal. So I'm going to find the voltage at this node, which is this one here, which is the same as this. Connected, the same as this. They're all connected to one point, so there is one voltage here. I'm going to call this voltage V1, and this is the reference here, which is actually grounded, so V0. Okay. So I have one node plus the reference node. So I'm going to use the nodal analysis, find one equation, find the voltage V1, then use that voltage to find E Thevenin. So I'm going to use nodal analysis here. As I said, you can use any technique just to find the voltage between these 2 points. So at the node, I have current here. I'm going to assume it's leaving. Let me change the color so you can see it. Current here, I'm going to assume it's leaving because I don't know. Leaving the node like this. Then here, I know the current is leaving. I know the value. So I don't have to guess or assume. This open circuit, current here, I know it's an open circuit, so it's 0. And the current here, I'm going to assume it's leaving because I don't know it. So I have 4 currents, all of them are leaving. So sum of the entering currents, this is at any node, Kirchhoff's current law, equals to the out currents. So entering currents, no. Leaving currents at this into this resistance is V1 minus 0 divided by the resistance, which is 5.6K. Then the second branch is 0 because it's an open circuit, no current going through. The third one, it's 8 milli. Then the fourth branch going this way. So it's leaving the node V1 minus the voltage after the resistance, which is 16, divided by 2.2K. So the voltage here is 16. The voltage at this side is V1. The voltage across the resistance is V1 minus 16, divided by the resistance gives you the current. Now I can multiply by 5.6K, for example. Okay, 5.6k. So 5.6k, we're multiplying it by everything. You can do any technique. So what will happen when we multiply by 5.6k, this cancels out. This will be multiplied by 5.6k, means times 10 to the power 3. And this is going to be multiplied by 5.6k. So 0 equals to V1 minus 0 plus 0. When we multiply this by 5 by 6k, the k will cancel the milli. 10 to the negative 3, 10 to the power 3 cancels out. 5 times this is 40, and that is 44.8, I think. Then here, 5.6 divided 2.2, I don't know how much is that. Can anyone give me the answer? 5.5 divided by 2.2. The k will cancel out with the k.
2.5.
2.4. What is after the 4?
2.5.
2.4 what? 5 what?
Amps, milliamps.
No. Give me 3 digits, please.
I only got 2.5.
2.5 exactly?
Yes.
Okay, 2.5 V1. Okay, because when you cancel out this by this, you get 2.5. Then 2.5 times 16, that is 40. So we're gonna try to do this. 0, V1 and 2, so 3.5 V1. And 44.8 minus 40, that is a plus 40 plus 4.8. So from here, V1 is going to be this divided by this. So negative, because it goes to the other side, 1 point, I don't know how much is that. Give me a solution. Use your calculator next to you. So this is 2.54. Okay. This means there is 4 here. Okay. So then 4.8 divided by 3.54. 1.35 maybe volt. I waited so much, but no one gave me any answer. Anyhow, so this is 1.35 minus. So instead of writing minus, what should we do? We change the polarity here. Like this. Because it's minus, so it's flipped. please go through the calculation here. Go through the calculation one more time. Go through the calculation one more time and make sure that those numbers are okay. So this is actually for, oh, I forgot that this would be a little bit different. This 40 will be a little bit different because it's 2.54. So it is 5.6 divided by 2.2 multiplied by 16. This is 40.72. So that means this number and this number will be changed. Guys, when you use, so this is going to be 4.08. This is 1.15. So this is 1.15 volt. Now I can see there's about 20 students in the class. No one except one guy gave me the answer for a basic calculation. So please work with me. Please work with me. When you look at it, maybe too difficult or too easy. When you try it, if it's too difficult, it's going to be easier with the time. If it's too easy, you will find it's not that easy. You have to actually try it. Is this question okay? Is this question fine? Any questions here? Okay. So one more time. Whenever the question says find the Thevenin equivalent circuit, it means you have at the end to draw the equivalent circuit and say, here's the equivalent circuit. And this equivalent circuit is basically equivalent, this equivalent circuit is basically equivalent to this, except this part is not included because it's between the terminals. So this part is this one. And you can see the equivalent circuit is way easier to analyze. So if you change R and give whatever value for R, you're gonna find the current through it or the voltage across it very easy, while in the original circuit it's difficult. So the equivalent circuit is supposed to be an easy circuit equivalent to more complicated circuit. Equivalent means we'll do the same thing. Okay, we'll do the same thing. Whatever you connect in here, whatever resistance you put here, and you put here, you're gonna get the same current, same voltage, same power. The steps you find R Thevenin, E Thevenin. When you find R Thevenin, remove the sources, current source, replace it with an open circuit, voltage source, replace it with a short circuit. Find the total equivalent resistance, that is R Thevenin. E Thevenin, you have to find the open circuit voltage. The open circuit voltage between these 2 points is actually E Thevenin here. So in the original circuit, it should be an open circuit voltage. So it can give you this value. If the number is negative, flip the polarity. You see the polarity of the source here? It's flipped. Instead of this way, and minus 1.15, instead of writing it this way, what we do, we flip the polarity and we write it positive 1.15. And these two are equal. But this is nicer. The second one is nicer because it doesn't have the negative value. So negative voltage, it means just the opposite polarity. Okay, we're gonna continue. We're going to continue, spend so much time on this with this exercise, but I want you to try it while I'm actually taking the attendance. We still have one more, I think. Yeah. So try this one. Try this one. It's an AC now, so you have to deal with complex numbers. While I'm actually gonna do the attendance. Okay, I'm gonna call the names here. Abdullah Abdul Razzaq.
Yes, sir.
Thank you. Muhammad Mohsen.
Yes, sir, I'm here.
Thank you. Hassan Abu Hassan.
Yes, sir.
Thank you. Rand. Thank you. Yazan. Not here. Sarah. Abdullah Ali. Maryam Ahmed.
Here, Mr.
Thank you. Abdullah Ahmed. Ahmed Al-Tayyib. Khalid Ali. I think he topped the course. Asma Al-Khater. Thank you. Muhammad Yusuf.
Yes.
Thank you. Leen. Thank you. Fahad.
Yes, sir.
Thank you. Amal. Abdullah Hassan. Hazim.
Yes.
Samar.
Yes, Mr.
Thank you. Siyad Ali.
Yes, sir.
Awatif.
Yes, sir.
Thank you. Aisam.
Yes, sir.
Okay. Manal.
Yes, sir.
Thank you. Hamad. Asia.
Yes, sir. I'm here.
Okay, Hamad. Asia. Sharif. No. Ahmed Ayman. Taha. Okay, we will continue with the lecture.
Mister, I am Amal. Also, I'm here.
Amal, yes, I think you are here. We're gonna take the attendance one more
Sir,
time. So
I'm
yes,
Abdullah.
Abdullah Hassan.
Yeah.
Yeah, you're. I saw that you wrote in the chat. So okay, so we're gonna find the equivalent circuit, Thevenin equivalent circuit here. Thevenin equivalent circuit is a source, and so at the end, your answer should be the Thevenin equivalent. So equivalent to this, we mean, okay? So the Thevenin's equivalent circuit. Okay, it's gonna be impedance. Now it's different. It's gonna be impedance called Z Thevenin and source, and this time it's gonna be AC source because it's an AC circuit. So the equivalent source is gonna be AC source, not a DC source. And the source is called E Thevenin. And at the end, the resistance, the load, those are the points. The load is just added this R here. Okay. So for this circuit, shaded here in blue, this one will be the equivalent circuit. So two things we have to find. First, we're going to try to find Z Thevenin. Then we're going to find E Thevenin. So when we find Z Thevenin, we do the circuit, we remove those are the terminal. I have to know where the terminals are because I'm going to find the impedance between them. Then what I have this, and I have this capacitor, and I have the source. Same here is the same circuit. Have the capacitor, and those are the terminals. I'm gonna find the voltage here, E Thevenin, and I have the source. It's an AC source, 10 angle 0 volt, J8 ohm, and here J minus J2 ohm. See, we use impedance when we do the analysis for AC circuit. J8 ohm minus J2 ohm, and this is 10 angle 0 volt. So when we do the impedance, we're going to remove the source. So we're going to come to the source, remove it. It's a voltage source, so I have to replace it with a short circuit. This circuit, I do nothing. Now, when we look here, there are two impedances connected in parallel because this end is connected to this end, and that end here is actually connected to this end here. Parallel connected. So the total impedance is actually, you can do it this way, the way maybe you're used to. So this is J8, it's in parallel with minus J2, or you can do it this way as well, which is because they're two, you multiply, you divide by the sum. So it's J8 multiplied by minus J2, and the sum J8 and minus J2. This is gonna give me, J cancels out, 6 in here, and in the top is 16, so 16 minus 16 J over 6. That gives me minus J 2.667 ohm. So this is found minus J 2.667 ohm. Usually when I do the calculation, I consider minimum of 3 digits, okay? Minimum of 3 digits. So I don't write, for example, 2.5 only. I write 2.54 if there is a number here. This is 3 digits. Sometimes I use 4 digits, so maybe I write what is next. Like here, I used 4 digits. Especially when the numbers are small, I use 4 digits. So this is the impedance. Now, the E Thevenin is the voltage between these 2 points, here and here, which is the same as the voltage between these 2 points. Now, this is an open circuit, so I can draw the circuit. Oops. like this. (10∠0V), J8 ohm minus, I'm gonna write it here, minus J2 ohm. Now the voltage across this is E Thevenin. The voltage between these 2 points is the same as the voltage across the capacitor. I can use voltage divider because there is a source and 2 elements, or you can find the current and multiply it by the impedance of the capacitor. That's another thing. So I can say E Thevenin. I use the divider, so I'm going to multiply by this impedance, divide by the total, J2. Don't forget the minus, divided by the sum, which is J8 plus minus J2. So I'm adding them, multiplied by the total voltage, which is 10∠0. This is minus J cancels out with the J, minus 2/6. So this is gonna give me minus 10/3 angle 0. Let me write it 3.3, maybe better. If you put it in your calculator, now minus, it means 180 degrees, so I can say E Thevenin in another way equal to 3.33. You can write another one, maybe angle 180, because the angle minus, it means 180. Okay, volt. So I can come here and I say this is 3.33 angle 180 degree volt. And this is the answer here. Any questions? You can do this in a quiz. You can do this in an assignment. Now in the assignment, it will ask you for one thing. It will ask you for example, find the E Thevenin. And if it says find the magnitude of the E Thevenin, it means they only ask for this. The magnitude, this number. Find the magnitude of Z Thevenin, it's this number. Because this is in the polar form, means 2.667 angle minus 90. Minus J means minus 90. So J means 90 degree. Minus J means minus 90. Minus equals 180 degree. If it's a minus number, or minus 180 is the same thing. Any questions? Sometimes instead of writing impedance, because this looks like a capacitor, because it's minus J, someone can actually do the equivalent circuit like this. This is minus J 2.667 ohm, and this is 3.333 minus 180 volt, and this is the resistance. This is Z Thevenin, and this is E Thevenin. You can do it this way as well, because minus J only, it means it is a capacitor like this capacitor. So the total impedance, the equivalent impedance, is actually a pure capacitor here. So you do it this way or that way, both are fine. Okay, we'll go to the last question in this. Okay, I'll give you a minute here to do this exercise. Okay, try it, please. Draw the equivalent circuit. Okay, first. Then try to find here, since it's an AC circuit, try to find the equivalent impedance, the Thevenin equivalent impedance. And to do that, you have to remove the element between the terminals A and B, and you have to remove the sources. We only have one current source here, so you're going to replace it with an open circuit. Try it, please, try it. Okay, so the solution at the end, the last step in the question, will have to be finding the equivalent circuit, Thevenin. This is what the question says, and says external to the terminal. So what is between the terminals is not included. So the Thevenin equivalent is going to be impedance, Z Thevenin, and source. It's AC now, the circuit is AC, so the source is going to be AC source, E Thevenin. Those are the two that I have to find, so I can say this is the equivalent. Those are the terminals A and B. This is A, this is B. And that impedance in between is just connected here. So the impedance is not included in my calculation. It's out of my equivalent circuit. This is the include equivalent circuit. So this is 32 ohms and it is XC. So two things. We're going to find Z Thevenin and we're going to find E Thevenin. So for E Thevenin, the circuit is the same, but we remove the terminal, what is between the terminals. So I have this. Those are the terminals. Between them, I'm going to find the open circuit voltage. Open circuit voltage It is the open circuit voltage. So in a lab, you just bring a voltmeter and measure between these 2 points. It's actually easier in the lab, except that you have to find the angle if it's AC. So you have to use a oscilloscope. 68 ohm. No, this is 20 ohm. And this is J20 ohm. And this is the current source. 10 angle 0 ampere. Here for the impedance, I'm gonna use the circuit like this. Again, the terminals are open. The impedance between them, I have here the branch with the resistor. I have a branch here with the resistance and inductance. Then I have the source, the current source. So this is 20, 68. This is J20. So what we do when we find the impedance, we're going to remove the sources. So this source is a current source. We'll remove it. I leave it open circuit. Now the open branch is not going to affect my analysis. The open branch, this branch can be removed completely because there's nothing going through it. No voltage drop, no current going through it. Infinity impedance. So I can actually say, okay, this circuit, I can make it look nicer. Okay. So the 20, the J20 ohm, the 20 ohm. Then see, this point is the same as this point, is the same as this point. So I'm gonna just put the impedance, the resistance here like this. And those are the 2 points A and B. And between them is the impedance. So I just moved these two here, which is the same point. This point is the same as this point. This point is the same as this point. So I can actually put them here. Now the idea that these two are connected in series, so I can consider them one impedance connected in series with this one and parallel with this one, sorry. That's another one. So you can say Z total is actually 20 plus J20 in parallel with 68. So you can do it the way you want. Z Thevenin. You can multiply, divide by the sum. So this multiplied by this and this plus the second one. 68, 68, 20 plus J20, 20 plus J20. Anyone can give me the answer for this? Answers. or I should take it 21.31, 32.7. 21.31, 32 point something, I don't remember now, 0.1 ohm. So this is 21.3 angle 32 ohm. You can make sure that it is the right value. Plug this in your calculator and get the answer. I got Sam giving me the answer in the rectangular L, which is 18 point, and that is 4 plus J 11.36 ohm. So you write it in the rectangular form or polar form, they're both fine. So they're both fine. Now when we do this analysis here for the Thevenin, usually look at the circuit. If I have one node, I use nodal analysis. So I'm going to use nodal analysis again. So this node is actually the ground. You can use mesh, you can use other techniques, whatever technique you feel is the easy technique. So this is V0. This is the node here, which is the same as this, the same as this, and the same as this. I'm going to call it V1. 4 branches connected, 1 current is coming in. This is coming to the node. This one I don't know, so I'm going to assume it is leaving. This one, it's an open circuit, so it's 0. And this one I don't know, so I'm going to assume it's leaving. So sum of the coming currents, 10, angle 0. Leaving currents, there's 2 leaving current. This is 0, so I can just write it here, or that's it. So 1 leaving here, V1 minus 0 divided by the total impedance. This is considered one impedance, which is 20 plus J20. And the voltage across it, from one side is V1, from the other side is 0. Then the 68 ohm, the current going through it is the voltage across it divided by the impedance. So the voltage across it, from one side it's V1, from the other side is 0. So this is 10, angle 0. You can take V1 as a common factor, because the 0 and the 0, they're not nothing. So what you have 1 over, this is 20. 20 plus J20 plus 1 over 68. So I took V1 as a common factor. The 0 is, just remove it, it's nothing. So it's V1 over this, V1 over this. I took V1 common factor, so I have 1 and 1. So if you multiply it in, V1 times 1 gives you V1. V1 times 1 gives you V1, so it gives me that back. Now I want to find V1, so I'm going to do V1 equals to this divided by this. So 10 angle 0 divided by the values here, which is this plus that 68, 20 plus J20, and this should give you the answer. I think it's 213, I remember from going there, 0.1 and angle 32, I think, volt. Now Thevenin is the voltage between here and here. Okay, it's the voltage between this point and this point. The voltage at the top is V1, so Thevenin is the difference between the voltage at A and B, between A and B. V at A is V1. And at B here is the ground, is the 0. So basically equals V1, which is 213.1 and angle 32. Just write it here, 213.1 angle 32 volt. And this is the answer for this. This is the equivalent circuit for the circuit in the question. Any questions here? You have to be okay with complex numbers. You have to be able to solve some basic equations like this equation here for finding V1. Do whatever technique to solve it. It's one equation with one unknown. You can find the common factor, you can find the common denominator, you can find whatever, solve it. Any questions? Quiet class. Remember, you have to do the assignment today. Do it several times. It's due tomorrow at 6 p.m. So you still have tomorrow, but it would be a good idea to try it today, so just in case you have a question. The other thing, that there is a quiz tomorrow at 8 o'clock. I'm going to send an email today about that. Done with lecture 5. We're going to go to lecture 6. No questions here? You know, no questions is scary. Means you guys either understand or you don't understand nothing, even you can't even ask question. Is this easy? Is this difficult? Someone has to say something. Abdullah, is this easy, difficult? Asma, Awatif, Fahad, Hamad, someone has to say something. Say
Not
something.
that much easy.
Okay. Okay, say something, guys. Say this is okay, this is too difficult. Okay, we'll go to the next lecture. So next lecture, lecture 6, is exactly the same. So before we go, I'm gonna just tell you what it is. So in this lecture called Thevenin equivalent theorem, okay, we find equivalent circuit that is like this. Or if it's a DC, like this. Now what we're gonna find a circuit called Norton, and it is basically just the current source. Or it is like this if it's a DC. So the equivalent circuit here is current source in parallel with impedance. What's the relationship between them? This Thevenin is actually equal to, it's the same as Norton. R in Thevenin is actually the same as R Norton. So the same way you find them. This is called I Norton. This is called E Thevenin. It's just the name of a guy. This is E Thevenin, and this is I Norton. So this impedance or this resistance is exactly here and here, just a different name, but the way you find it is exactly the same. So that is nothing new. Now the relationship between this current and this voltage is Ohm's law. So IN basically E Thevenin divided by the impedance Thevenin. Or in this circuit, I Norton is E Thevenin divided by the resistance Thevenin in the DC. So if you have this equivalent circuit, it's easy to find this equivalent circuit. Now, E Thevenin is open circuit. Ouch. Voltage. I Norton, you can't have open circuit current. There's no current in that case. So it is short circuit current. So you come here, you put a short circuit, and you measure the current. It's a short circuit current. So let's say that you want to find Thevenin equivalent, you find it, let's say. Or you find it difficult, you find the Norton equivalent, then you switch it to Thevenin. That's totally fine. So if you have Thevenin, you don't have to do the procedure one more time to find Norton equivalent. You can just source a transformation, if you remember the source transformation, from a current source to a voltage source or the other way around. So we're going to go through the Norton equivalent and we're going to see that it is similar. At least half of the question is the same, finding the equivalent impedance or resistance. I'm going to share the lecture with you guys and we will go through it. So now Norton's theorem, the same idea, but it's different source. So it says any linear network that has two terminals can be replaced with equivalent circuit, an easy equivalent circuit. And this circuit is a current source now in parallel with either resistor or impedance. So this is now Norton's here. The procedure is quite similar, except one thing at the end. So this circuit, I'm gonna find equivalent that looks like this. So first we're gonna remove the portion of the network, okay, that between the A and B. So that is not included. We always remove it. Then we're gonna find R Norton. You see the writing is exactly the same. It's a slide, it just this time is called Rn, but it's the same thing. We're gonna remove the sources, short circuit for the voltage source, open circuit for the current sources. Then we're gonna find the total resistance between the terminals. Dependent, we don't do dependent sources in this course. IN now, before we find E Thevenin, now we find I Norton is the short circuit current. So you're gonna put a short circuit between the terminals and find that current. Then the last thing, you have to draw the equivalent circuit, because if the question says find the equivalent circuit, you have to give them the equivalent circuit, not just bunch of numbers. See, the same idea. This is the question we had before in that exercise, in that lecture. Finding our Norton is the same thing. So what we remove this, so it's gone because it's out. This is just a load. Then the voltage source we replaced with a short circuit. This is what we do. We find the total resistance. These are in parallel. You multiply, you divide by the sum, you get 2 ohm. So that is one thing. Now the second thing, I short circuit, is what we do. We short between the terminals. We put a short circuit and we find the current. Now any element that is shorted is gone. Okay, so this element is shorted. Any element that is shorted in the circuit, you can remove it. So basically this, there's no current going through this because there's a short circuit across it. You see the short circuit is across it. So when I want to find, now I'm going to find the current going here. That is the Norton current, the short circuit current. So the circuit will be like this. Three, 9. This is the short circuit current. This branch is gone because it's shorted. So what is the current? Is 9 divided by 3 is 3 ampere. In the lab, if you want to find the short circuit current, you're going to put the short circuit and put an ammeter here. Like this. Okay. So when you put the short circuit, then you're going to insert the ammeter. So you're going to remove this and insert the ammeter. So basically you don't have to put the short circuit. The ammeter will make the short circuit. So when you want to measure the current in between A and B, in the short circuit between A and B, just insert an ammeter between A and B and it will give you the reading. So the last step would be drawing the circuit. Now we have to remember it's parallel, okay, with the current source. The short circuit current, the Norton current, is a 3. The Norton equivalent resistance is 2. We draw the circuit, okay, and we know before that this is the Norton. If someone says find Norton and equivalent, Thevenin equivalent, you can just go to the Thevenin directly from Norton. R Norton equals to R Thevenin. E Thevenin, Ohm's law, is just I times R. So E Thevenin is I times R, Norton and Norton. If you want I Norton from Thevenin, you can just say E Thevenin divided by R Thevenin. And basically R Thevenin is the same as R Norton. But when we do Norton's equivalent, we don't write R Thevenin here. No, we write Norton. Okay. Even if it's the same thing, but we write it as R Norton. Here's another example. One minute, guys. Okay, sorry for that. I got visitors at my office. So okay, so we'll continue. Here's a question. Find the Norton equivalent circuit for the network. Okay. Giving that this is 20 angle 0. This is 4 ohm. And this is 12 ohm. Now, first thing you have to find the Z Norton. Remove the source, put the short circuit. These two elements are in parallel. This is J4. This is minus J12 ohm. You multiply, you divide by the sum, you're going to get the answer. So this is Z Norton here. So that's one element. Then we're going to find the short circuit current. That is I Norton. So to do that, we're going to get the circuit. We're going to put the short circuit here and find this current. Now, when you put the short circuit, this element is shorted. You can see there is a short circuit across it. So it's not part of my circuit anymore. You can remove it. Shorted element is not going to affect your calculation because there's no current going to go through it. The current is going to go through the short circuit. So what you have here, you have this and this and that one. And this is the short circuit current. This is I Norton. So remember again, Norton current, Norton equivalent current is actually the short circuit current between the terminals. So you short the terminals of the circuit, you put the short circuit there, and you find the current in that short circuit. Any element that is shorted, is gone. Shorted, it means around it there is a short circuit. Okay. So here, this is J4, this is 20 angle something 0. So the total current is just the voltage divided by the impedance, you get the current. Then you draw the equivalent circuit. This is the equivalent impedance. Remember, it was Z Norton, it was J6 ohm from the calculation. J, it means it's an inductor with 6 ohm reactance. And the Norton current, this is the value. So your answer at the end, it has to be the Norton equivalent circuit, and this is the equivalent circuit. When the circuit is complicated, the calculation is complicated, but the idea itself is not complicated. The idea is not actually complicated. You go through a few exercises and you should be really good with this stuff. Okay, here's an exercise, and I'm gonna give you a couple of minutes, and I'm gonna take the attendance one more time. Okay, so try to do this exercise. I think we have 4 exercises. No, 5. So 5 exercises and the answers at the end. I think we can do most of them today. Okay. See, this question, we found the equivalent circuit, the Norton equivalent circuit. Now we're going to find Thevenin equivalent circuit. Okay, try to do the first exercise, please. When I say try, please try it. I'm going to do the attendance one more time. So one more time, the attendance for the second hour. Abdullah Abdul Razak.
Yes, sir.
Thank you. Muhammad Mohsen.
Yes, sir.
Thank you. Hassan, Abu Hassan.
Yes, sir.
Thank you. Rand. Thank you. Maryam Ahmed.
Here, sir.
Thank you. Asma. Asma is not here. Okay. That means left early. That's what we do it. Muhammad Yusuf.
Yes.
Lean. Thank you. Fahad.
Yes, sir.
Thank you. Amal.
Yes.
Okay. Abdullah Hassan.
Yes.
Hazem. Hazem not here. Okay. Samar.
Yes, Master.
Thank you. Ziad Ali. Awatif. Awatif.
Yes, yes.
Isam.
Yes, sir.
Manal. Hamad. Hamad, you're around.
Yes, I am here, sir.
Thank you. Okay. Sharif. Sharif. Not here. Okay. Oh, Ziad, you're here.
Yes, sir, I'm here.
Okay, we'll continue with the class, with the lecture. Okay, sometimes it might seem confusing, but to try the question, I try to do the steps step by step. So I know that my end will be the Norton equivalent. So I have to do at the end, my answer has to be this, the Norton. This is the last step. But it's good to know where I'm going, the Norton's equivalent. Now this is a DC circuit, so I'm gonna have a DC current source, and it's IN, and I'm gonna have in parallel. Now it's in parallel, current source is in parallel with its own internal RN. Those are the terminals A and B. And at the end, that is just the 9 ohm resistance that's not included in my equivalent circuit. So I'm going to find equivalent circuit to this network, but the 9 is not included. It says external to that 9 ohm between these two terminals. So first thing I have to find are Norton. See, now I don't write Thevenin because it's Norton equivalent. And I'll have to try to find I Norton. The same procedure. When we find R Norton, Same procedure we do for our Thevenin. So what we're gonna do, we're gonna put the circuit. We're gonna put the resistor, current source, then the other resistor. Then we go back here. Our Norton is between these 2 points, A and B, between the terminals. So this is 5 ohm, and this is 4 ohm. What do we do with the source? We're gonna remove it. Open circuit. Now the open circuit branch is not gonna affect my analysis, so I can remove this branch between this point and this point. This is the branch here, by the way, between intersection and intersection. So the circuit will look like this if I make it. I removed the branch. This is the 5 ohm connected to the 4 ohm. I just removed that branch. Then from here you go through the 5, then you go through the 4, then you come back to the terminal B. So it's A and B. Now I can see clearly here Rn is actually these 2 resistors in series, so it's 9 ohm. So that is one thing. This is 9 ohm. So I'm like 60–70% done with the question. I'm gonna try to find I Norton, which is the short circuit current. Remember that. That is important to remember. You have to know that it is the short circuit current. So what I'm gonna do, I'm gonna find the terminals A and B, and I'm gonna draw the circuit. That is the 5 ohm. This is 10 ampere. This is the 4 ohm. And now what I want to do, short circuit is my short circuit, and find the current here, which is I Norton. Remember that you're gonna put the short circuit between the terminals and find the current in that short circuit. Okay, short circuit the terminals and find the current in that short circuit. Now I'm going to arrange this. I'm going to arrange this like this. Just rearrange the circuit. This is the 10 ampere source. Okay, coming here. There is a point here. It's 5 ampere ohm. And there is this one here. This is the 4 ohm. This is the short circuit current here. This circuit is exactly like that one. This point is this point, and this point here is this point. So you come this intersection, you go this way around through the 4 ohm, or you go this around through the 5 ohm. So what happens, the 10 ohm here is going to be divided into a current going that way and a current going this way. So I can use the current divider, I Norton. You know, the simple current divider when you have 2 resistors. If you want the current in the 4 ohm, you multiply by the 5 ohm. Then you divide by the sum. multiplied by the total. So here 50 divided by 9 is actually 5.55, I think, ampere. So the current here is 5.55 ampere. 50 divided by 9 is 5. Then you have 5 left. Yes, I think that's the answer. Is this question okay? Any questions here? Any questions? No? Things are okay? You can do a question like this? Okay, so we'll continue. We have 20 minutes left. We will do this question, then we will leave 3 exercises to the next class. Okay, so let's do this and will be the end for today. Or maybe we can do one more. We will see. Okay, so again, find Norton equivalent circuit of this network and left to the terminal. So this is the RL is not included. Then once we find the network, we can actually connect different resistors in the equivalent circuit, which is an easier circuit, and we can find the current here. So if we connect 6 ohm here, it's difficult to find. Then if we connect 10, it's difficult to do the analysis. 30, difficult to do the analysis. So we're going to do the equivalent circuit, which is going to be, this is the answer at the end, the Thevenin, oh, Norton here, sorry, the Norton equivalent circuit. So the Norton equivalent circuit is actually going to be a current source, and this is a DC circuit, so it's going to be a current source in parallel with impedance or resistance. Now it's DC, so it's resistance Rn. This is In, and those are my terminals A and B. Those are the terminals of the original circuit, and I can connect the RL now here, which is external to my circuit. So 2 things, I have to find Rn, and I have to find In. So to find Rn, I'm going to put the resistors with no sources. So those are the terminals A and B. I'm going to try to find Rn between them. Looking into the circuit, I have the 1 ohm, then I have the 4 ohm, I have the source, then I have the 12 ohm, and I have the other source. Then this all together comes to this point. 1 ohm, 4 ohm, 12 ohm, and current source, voltage source. So what do we do to the sources when I want to find Rn? The sources basically removed. Current replaced with an open circuit, voltage replaced with a short circuit. So I'm going to put the short circuit here. It means 0 volt. This is what we did for the same question last time. And I'm going to try to make it look nicer. The branch, the open branch, this branch here is gone. Even if there is a resistor here or source or whatever, it's an open circuit, خلاص. It's not going to affect the total resistance. So the 4 and 12 are connected in parallel. You can see that clearly. And this 1 ohm is added to them, to their combination R, Norton, looking this way. So I'm going to combine, this is the 1, these two together. Let me change the color so can these two together. They will be one equivalent resistance. This is Rn. It's going to be equal. This is 3 ohm here, and this is 1 ohm. So 4 times 12 divided by 4 plus 12, that is 3 ohm resistance, and this is the total for this guy. So this is just this, and Rn equals to 4 ohm. We found this one, 4 ohm. We're gonna do the IN. So IN basically is the short circuit current. Remember that, short circuit current. So between the terminals A and B, between the terminals where we want to find the equivalent circuit, we're gonna put a short circuit. So I'm gonna draw the same circuit. For 12 ohm. This is 2 ampere going up. This is 1 ohm. These are the terminals A and B. So what should I do here? I'm gonna put the short circuit, and I'm gonna put the current going here. And this is my Norton current. Now, how can I find this current? Maybe I should use nodal analysis. It's the analysis that I like, but you can use anything else. So I'm gonna use nodal. I'm gonna put this as a reference. Okay, V here equal to 0. This is connected to it. This is connected to it. This is still the same node because it's connected, no resistor, nothing, no drop here, and this is connected to it. So this is all 0 volt. Those points, they're all 0 volt. Now this is a node. I'm gonna call it V1. This is connected to it. This branch is connected. There's nothing here, so this is still the same node. So this is one node. This is basically just one node because there's nothing in between the two intersections. Now, how many branches are connected to these nodes? There is this branch, current I don't know, it's leaving. This branch, current I don't know, so I'm going to assume it's leaving. Current here I know, and it's actually going to. Current here I don't know, which is I'm going to assume it's leaving. By the way, this is the current IN. So 4 currents here, 3 are leaving, 1 is coming in, so 2 is coming. The leaving in the 4 ohm is V1 minus 32 divided by 4 plus the current in the 12, V1 minus 0 divided by the 12. The voltage here is V1, the voltage at the other side is 0, plus The current in 1 ohm here, V1, minus 0 divided by 1. This current here, V1 minus 0 divided by 1 is IN. This current is IN. So this, if I write them as a current, this is I1, let's say. This is this one. This is I2. This is IN. It's this current. But I don't use this equation, I use the nodal equation, that one up. So I'm gonna multiply this equation by 12, so we can solve 24 equal to multiply by 12, so divides 3, so it's 3 V1 minus 96 plus V1 plus 12 V1. So here I have 120 equals to 16 V1. So from here V1 will equal to 120 divided by 16. What is that? Any answers? 120 divided by 16, so 7.5? I think it's 7.5. Because 5 is 80, 7.5 volt. Now, I found the voltage here, 7.5. I want the current IN. IN is the current in the 1 ohm resistance, this current, which is basically V1 minus 0 divided by the 1 ohm resistance. So equals to 7.5 ampere. So this is 7.5 ampere. The current here in this branch is IN. The voltage at this point is 7.5. The voltage here is 0. Cross this resistance, the voltage is 7.5 minus 0. 7.5 minus 0. If I divide it by the resistance, it will give me the current going through the resistance. Ohm's law. Now it says at the end, if you have RL equals to 6, find IL. So I'm going to use the simple circuit current divider here. So IL, I want, this is 6 here. So I'm going to multiply by the other resistance, 4. And this is 4 plus 6 times 7.5. This gives me 30 divided, so 3 ampere. If the resistance RL equals to 10, IL will be 4 plus 10 multiplied by 7.5. I'm using the current divider here, which is going to be 30 divided by 14, 2.14 ampere. If RL equals to 30, IL here will equal to 4 plus 30, 7.5. I think this gives me 0.88 ampere. If you go back to the lecture 5, you're gonna see the same question. You're gonna see that the equivalent circuit we found there, Thevenin, is the resistance the same, 4 ohm, and the source is 30 volt. Okay, and this is RL. So if you have that resistor, that circuit, you can easily find this one. 4 is the same as the 4. This current is 30 divided by 4, which is 7.5. And once you connect different loads here, RL, you're going to see when we connected 6, you get the same current. You're going to connect 10, you get the same current in the Thevenin circuit and the Norton circuit. It's going to be the same answers. It means actually these two circuits are equivalent to each other, and they're equivalent to this circuit. Even in this circuit, if you connect values here, the loads, you're going to get the same currents. Okay, so this is the end. We'll have 3 exercises left in this lecture. I'm going to put the lab on lab number 5 on D2L later today. So you can actually look at the lab and you can actually do the simulation online. You can actually do the calculation, okay, which is going to be Thevenin equivalent, okay, circuit. And if you have issues, let me know so you can go to the lab ready. Once they give you your own values, you just do the same procedure and do the lab. It should not be difficult. But if you have issues, let me know later. Please do the assignment and be ready for the quiz tomorrow. Any questions?
No.
Okay, if you guys are good, I'll be at the college. I'm actually at the college, but I have class until 10:30. So if you're around and you have questions later today, I'll be around maybe until 4 o'clock or something, 4:30. So if you have questions and you're around, you can come by. And then, Assalamu alaikum.